Okay, this video is on discriminant analysis. It's kind of the video that you've all been waiting on because it's the last one of the sequence of 6610 and 6620 and a 6999 course. This is the last thing I want you to, well, it's not the last thing I want you to know, but it's the last thing that I'm going to at least try to teach you and make you aware of. It turns out discriminant analysis is a powerful tool in ed research, and it kind of hints the reason I want to throw it in here at the last in the last week. For validation research, we often have a goal of preparing a procedure for using test data to categorize examinees in two or more groups. An example we run into sometimes with a placement test is we may want to create a procedure, a model that can discriminate between those who need developmental or remedial math versus those who don't. Or we may have a reading test that we would like for it to be able to discriminate between who we would classify as a poor reader, a mildly poor reader, average reader, or superior reader. Now the focus here is I want you to realize that as we bounce this new technique called discriminant function analysis off multiple regression and logistic regression, keep in mind here that the classification procedure can be over 2, 3, 4. The reading test example there that we have actually is trying to discriminate across 4 groups. So, guys, the process of this discriminant analysis is again with scores on a sample of examinees for whom the correct classification is known. So previously with the placement decision, we would know based on something else whether the student was developmental or not. And based on their reading, we would know whether they were a poor reader, an excellent reader, whatever the classifications were. The second thing we do is we create what's called we calculate what's called the discriminant function. Now, you may think, if you're paying much attention here, that there's clear similarities between discriminant function analysis, logistic regression analysis, and multiple regression analysis. Now, the difference here lies much more strongly between discriminant function analysis and logistic regression than it does with multiple regression. Multiple regression is seeking to predict a particular score. And if we think about that score, it's I would say think about it as more to predict like a criterion score. Where logistic regression and discriminant function analysis seek to predict, explain, come up with a model, yada, 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 that defines group membership. Okay? So they're very, very, very closely related, but the more you learn about them, you find that there's huge differences as well. Now, what is the difference? And guys, from here on out in this video, except when I get into showing you how to do these on R and actually working a couple of problems, all this, the rest of the PowerPoint, I will say, I got out of the book Tabischnick and Fidel using multivariate statistics. So this is according to them, and you know, I agree completely. Not that they care what I agree with. Okay. Taking a quote from them, logistic regression allows one to predict a discrete outcome, such as group membership, from a set of variables that may be continuous, discrete, dichotomous, or a mix. So logistic regression is very flexible in that it puts no restrictions on the predictors that you use. So if we're trying to predict whether or not someone is going to succeed in a class, we could use a continuous predictor like ACT. We could use a discrete predictor, you know, possibly freshman, sophomore, junior, senior. We could use a dichotomous, male or female, or we could use some sort of interaction. We have complete and total flexibility on the set of variables that we're using to try to come up with a model that we can distinguish between group membership. Discriminant analysis, on the other hand, the goal of discriminant analysis, again, quote unquote from their textbook, is to predict group membership from a set of predictors. Now this should be, I actually made a typo here, it should be from a continuous set of predictors. If we have predictors that are dichotomous, predictors that are categorical in any manner, discriminant analysis is not the tool for you. Okay? Now, clear as mud, right? We're trying to predict group membership. What's the difference? Well, it turns out that the two are very, very, very similar, and I believe, and I didn't get this from Tabishnik and Fidel, I got this from just what I think. Logistic regression, I think, is better suited when the independent variables are not all continuous, and the dependent variable is dichotomous. And I think discriminant analysis is better suited when the dependent variable has more than two groups, and all of the independent variables are continuous. So it's if you have a output, a response variable, a dependent variable that's dichotomous, and your continuous, your predictors come in all shapes, forms, and sizes, and all it takes is one that's not continuous, then logistic regression is the tool. Now, there is something called ordinal regression, which is an extension of logistic regression, which allows your dependent variables to be ordinal, categorical ordinal variables. In that situation, I would far rather use discriminant analysis because it's just a simpler process. Logistic regression, again, it's very flexible. The dependent variable needs to be two mutually exclusive groups. Fail, succeed, live, die, true, false, this or that. It's much more relaxed and flexible in its assumptions because it deals with maximum likelihood estimation and not least squares approach as we run into with multiple regression. And the independent variables do not have to be normally distributed, linearly related, that's hard to say, nor have equal variances. So logistic regression is very, very flexible in its underlying assumptions. The issues with logistic regression is it requires larger sample sizes. I think of at least 50 cases per independent variable. And you got to think about dummy variables from way back in 5500. If you wanted to use as a predictor maybe socioeconomic status, or let's just say we want to use region, northeast, southeast, northwest, and southwest. And so you have a categorical predictor with 4 groups. Well, you're going to have to create your reference group, and you're going to have to create 3 predictors for each comparison. May want to motivate you to take a look back at the dummy variables. So in that situation, even though you've just got one predictor variable, or at least you think, which is called region, because of the nature of needing to create dummy variables, you would actually have 3 variables because you would have whatever your comparison group is, let's just call it northeast, you would have the southeast to northeast, the southwest to northeast, and the northeast, northwest, whatever. I got confused there. So you'd have 3 comparisons, so you would have 3 variables. So you'd have to have at least 150 cases to make that work. So guys, the rule of thumb, use logistic regression when the dependent variable is dichotomous and there's sufficient sample size. Okay? Discriminant analysis, when the assumptions regarding the distribution of predictors is met. The literature shows that discriminant function analysis may be more powerful and efficient. And again, when all things equal out, research has shown that discriminant analysis may very well provide more accurate classification. So discriminant analysis, at the end of the day, Let's use that when we have more than two mutually exclusive categories in the dependent variable, and the assumptions on the independent variables are reasonably met. Okay. Now I've got a couple of. I'm going to close this down, and I've got a couple of examples here. A couple of data sets. Now the first data set I got here is just something that I collected from some placement data, and the beauty I think of this example is this would work in logistic regression or discriminant analysis, because what we're doing, we're trying to predict group membership. The D turns out to be developmental math, and CR was college ready. And there's these arithmetic, ratio, measure, and algebra scores that were taken from a battery of kind of cumulative measurements that was put together to come up with these particular scores. So this one subject right here was known to be accurately classified as a developmental math student, and they scored a 1.9 on the arithmetic, a 4.3 on the ratio, and so on and so forth. This student down here, the 10th student, was accurately deemed to be college ready, and that person had an 11.8 on algebra, and so on and so forth. So we could use discriminant analysis or logistic regression, at least theoretically, but logistic regression wouldn't be an option here because we have 4 predictors, and we would need a sample size of 200 cases to be able to pull off logistic regression. So discriminant function analysis would be perfect for this. So guys, let me show you how this is run on R. It's a cool strategy, and it's something that we can use a lot when logistic regression sample size isn't met, or we severely violate assumptions. But again, discriminant analysis is restrictive too, because we can't have independent variables that are categorical. All right, gang, first thing you'd want to do is, and you should have installed this package recently, the mass package, but if not, or if I have, just access the library. And let's set our working directory. And then we'll go get our data. And I think I called this dichotomous.csv. I did not call it dichotomous.csv. What did I call it? DISC. Okay, that's weird. And attach our data. And something we can do here, if we want to head data and look at like the first 4 rows, we can use head and just tell it we want to use our data set data, and the 4 tells us the first 4 rows. So we can see that that we have our data that we examined in the spreadsheet. All right, it turns out to run the model, man, this is really easy once you get the mass package installed. There's a command that's LDA, and this stands for linear discriminant analysis. And the way that we enter this is just like we would do with multiple regression. And I'll tell you what, let's just leave it at that for now. Okay? Now, to take a look at our hard work, what we can do here is just type model. And what this will give us, it'll first of all give us our prior probabilities of groups. So right now, choosing, because there were 5 students who were developmental and 5 who were college ready, so if we choose one of those randomly, the probability of group membership is 0.5 for each. Next thing we get into is we get into group means across the arithmetic scores as presented across those that are college ready and those that were deemed to be proven to be developmental. And then we get into the coefficients of our linear discriminant model. So this is our discriminant model that we talked about a little bit earlier. Right now, nothing really too entertaining, but what we can do is we can do some predictions from this. And this is where things really get kind of cool. And there's a function called predict that's built into the math library. And what we can do here is we can access our model. And I want now to just look at our data. But I only want to look at 2, 3, 4, and 5. Now what this does is when I go data with bracket, this first part before the column allows me to select particular rows I want to look at. Well, I want to look at all the rows, so I have, I think actually I should put a space there. The second thing allows me to choose the columns. Well, I only want to predict based on the arithmetic ratio measurement in algebra. So this is the second, third, fourth, and fifth columns. So I want to isolate those. Okay? Now the next thing I do outside the parentheses is I'm going to do $class because I want to predict group membership. Right? So when I do that, I can get. It would seem reasonable to hit to type predict. It really doesn't help us much, but what it does is it gives us the group membership of each of the participants. So based on our model, we not only have the group that they actually placed in, in real life, we now have what our model actually predicted. Okay, and a really cool way to look at that, there's actually a couple of cool ways to look at it. One thing we could do is just create a new data frame and take the group and take the predict. And you'll see what happened is the very first subject I'm sorry, that was a developmental student, and they were now this let me point something out. That doesn't no, it actually does. Okay, the group actually does coincide with the way the data is presented. So what you can see here is, for example, the student number 5 who was found to be developmental, our model actually predicted that person to be developmental. And this person who was predicted to be, was deemed to be college ready, our model predicted that person to be developmental. So there's a discrepancy there between what was kind of observed and what we actually predicted. Now, it kind of goes back to the kind of things we talked about with chi-square, so to speak. Well, a really good way, and keep in mind we have a sample size here of only 10, and it's really easy to examine, and we can see that 9 out of 10 people were accurately classified according to their prediction using our model. So we have a classification rate of 90%. But imagine having a situation where you had maybe a large data set, maybe 1,400. A way to look at the output would be to take the predict and then to take our data and focus that solely on the first column, which is the group. And what that does, it gives us a classification table, and we can see of those who were actually college ready, 4 of them were predicted college ready. Of the ones who were developmental, 5 were predicted developmental, but there's one that's not. So our classification rate would be 90%, because you can take the CR column, the intersection, and the DD, and so 9 out of 10 were accurately classified. Now, that's kind of cool. It gives us something for kind of a basis of discussion, but you got to think about the just inherent issues with testing classification of a model that was created from the people that we are classifying. Right? Hope that makes sense. Our model was made on these 10 people. Our classifications were based on those 10 people. Our model was created from the 10 people that we're actually basing our classification on. Well, to me, that's almost cyclic logic. It just doesn't pass the smell test. So guys, we have clear issues with basing our classification of data from our model. Now, a couple of rules of thumb, actually 3 rules of thumb, things that we can do to address that. Some people like to create the model, and then when they do their predictions out here, they like to bring in new data. That happens a lot in health sciences. Another way of doing it is to split the data. So split your data into half, create your model, and create your classification table based on the other half of data to put that information in your model and actually set up your classification. So what I may end up doing here, and I'm not going to, but let's say I want to create a model 2. And what I wanted to do here is create LDA, and I want to do my group over all of my predictors, and I'm just going to go ... because I'm not going to make this happen. But I want my data to be only 1 through 5. But I want to use all of my, let's see. Yeah, so I would want that. So what I would do there is I would only create a model based on maybe the first 5 subjects. Now, obviously I'd get a horrible model because all first 5 subjects were in the group D. So I'd want to come up with some way where I get a random sample, and that would be really easy to do. There are ways you can do that in R. And then I would kind of get my classification based on putting the other half of the data in the model and seeing the classification. Another way is something called CV. In our language, the CV turns out to be what we call cross-validation. And cross-validation is something I'm getting ready to show you. And it's an acceptable way to actually predict or to come up with classification rates. And what it does is it will leave out one of the, it'll run the model, but it'll leave out in creating the model, it will leave out the person that you are making the prediction for. Now, it's really, really easy to do. I'm just going to scroll back up here to get my model. And so I'm going to come up here and actually do a model that's much more acceptable. And so I'm going to just call this model 2. And gang, I'm going to use the same thing here, but the only difference, I'm going to go CV equal true. So this is that cross-validation. And again, cross-validation is nothing more than it removes or it leaves out one of the people that we're actually making the prediction of. Okay. Now, model 2 is going to be provided here, and it gives us some different types of output. But what I want to do with this is I ultimately did the Model 2 so I can examine the classification rate. So I want to be able to look at a table here, and I want to look at Model 2, and I want to look at the class, obviously, and I want to look at this over my original. Let's see. Yeah. Now you'll notice here that the classification percentage has gone down. And so to calculate the classification percentage, I would see that 3 were appropriately classified under college ready, and 4 were appropriately classified. So I know we can do this easily mentally, but we would do our classification rate at 0.7. So we have a 70% classification rate using the cross-validation method. Now again, another way to do that is to split in 2 random halves. Split your data set in 2 random halves, create your model, come up with predictions on the other half of your data. That's completely and totally an acceptable way to address that. All right. So, guys, just like everything else we do, you're not going to be an expert in this, but it's one of those procedures that I want you to have on your radar. All right. All right, gang. Via power of video, you're probably thinking now, what's going on here? Because R looks completely different. What I've done is I've closed R down and I brought up a new data set here. And this is called, the data set is DISC2. And I think this is a more appropriate illustration of discriminant analysis. What I've done so far is I've just brought up the first 5 cases, but I think for illustration reasons, it would probably be better to go ahead and look at the entire data set. So you can see we have 150 cases. And the data we have on these cases are 3 groups, groups A, B, and C. So for example, the 50th subject here, we have evidence, we have those 4 scores, X1, X2, X3, X4, and we have reason to believe that that person should be in group A. This person down here, group B, and you'll see that there's a group of subjects in group C as well. So what we'd like to be able to do is we'd like to be able to come up with a discriminant function analysis for classification. Okay? Now, let's see what we can do here. The first thing, let me make sure, I don't know if I've, yeah, let me go ahead and access mass like we need to. And we have our data in, so the very first thing I'd want to do is just go ahead and cut to the chase and run my model. Again, linear discriminant analysis. And here I have class tilde x1 plus x2 plus x3 plus x4. And that's all I want to do right now. So when I run model, I'll get some cool stuff. The prior probabilities of these groups is clearly 1/3 because we have 3 groups. We have group means provided over the independent variables x1, x2, x3, x4 in the groups. That's sometimes helpful. But down here we get the coefficients of the linear discriminant model. And what will happen, dependent on the number of groups that you're trying to discriminate across, if you think about the example that we just did, we only had 2 groups, college ready and developmental. Well, when you calculated your coefficients for the linear discriminant model, you only had 1, LD1. To make a long story short, the number of groups you're trying to discriminate, the model you're trying to accurately classify across, So however many groups you have, you will always have n minus 1, or we usually talk about groups as being k. You'll have k minus 1 discriminant models that R will produce. Now it turns out in this case that one of our models is really good and one of our models is really, really bad. Something that R gives you down here, proportion of trace. If you look under LD1, this 0.9912 tells me, and I'll write this out so it's clear. This tells us that 99.1%, well, using model 1, that 99.12% of the between variance. Guys, I got something going on outside again. Okay. So using model 1, 99.12% of the between variance is explained. Second thing, using model 2, only 0.88% of the between variance is explained. Now guys, let me explain to you what I mean by between variance. What we're trying to do is there's variation between these groups A, B, and C. And why are some students placed in group A, some in B, and some in C? Well, the variance in that group selection, the first model explains 99.12% of that variation. Again, why do students go in one group over another? Why does group membership vary? Well, Model 1 explains 99% of that, and Model 2 explains just under 1%. So guys, right now I have tunnel vision on LD1. So our model is class equal 0.83 times x1 plus 1.53 times x2 plus, minus 2.20 times x3 minus 2.81 times x4. Okay? Now, so that's the model that we're going to use, and I'll get into that a little bit more in this video than I did the last video. So gang, we've created our model here. The next thing I want to do is be able to use our model to predict group membership. So I'm going to just call this predict again. And I want to make my predictions based on my model. And the data that I want to use is I want to use all the rows, but I only want to use the, fifth column? Yes, fifth column. And $sign. I got to tell you, I'm distracted by something going on outside. Okay, so these are our predictions, and it's really cool to take a look at our table. So we can do our table of our predictions over our data of all rows but the fifth column. Okay, now we get into percentage of accurately classified cases. So for A, I had 50 accurately classified cases. For B, 48 were accurately classified. And for C, we had 49 that were accurately classified. We had a total sample size of 150. So guys, you can see that we had 98% our model predicts group membership at 98% accuracy. Sometimes this is referred to as PAC, the percentage of accurately classified cases. You see that a lot in SPSS outputs for logistic regression. So that's kind of cool. But there's an inherent flaw, as we talked about in the previous video, because these predictions are made on cases that created the model. So it's almost, again, like a cyclic logic. So to correct that, what I want to do is I want to go back up, and I want to do this again, but I want to call this model 2. But in this situation, I want to use CV equal true. So we're using, as we talked about a while ago, we're using this. Keep wanting to call it circular value, cross validation, where we leave one out and leave out a case, and then make our classification based on that. Let's look at model 2. It's not going to be as interesting an output when you actually use the CV equal true, but nevertheless, it's going to lead for a basis for us to probably get more accurate classifications on prediction. Now, what I should be able to do from here is I should be able to do this, just table model 2 and do class and just look at my data on the 5th. Yeah. Okay. Now, what should have happened? I don't think it changed, did it? 48.2 and 49.1. Well, that's really strange, because usually that will change. I'll tell you what. Let me just make sure that I've got this right. I want to do a predict. I'll just tell you what. I'll go back up and get this. I want to do a second prediction on model 2. Yeah. Ah, okay, that's interesting. Why is that not working? Apply to an object of class called list. All right. Well, anyway, we took care of what we needed to right back up here, just using table and model 2. I'm kind of confused why that isn't working, unless maybe I did something silly. Oh, okay, guys, I know what it is. We can't follow up the predict with CV equal to true. You've got to do the percentage of accurately classified cases using this method right here. Now, something I want you to be aware of is that sometimes it's worthwhile to create a new, what we call discriminant scores. And what I may want to do there is I may want to just create the factor scores. And I want to go back up. I'll tell you what I want to do. I want to go back up and get my scores. Okay, yeah, I want that right there. So let's create our scores, and I'm just going to call these discriminant function y scores. And let's copy this and paste this right here. Let's not do that. Let's do this. I don't think this will allow me. Yeah, it actually does. All right. So let's create these scores and see if we can get some sort of pattern on classification. So what I'd like to do now is I'd like to create a data frame, and I want my x1, x2, x3, x4. I want my class, but I also want my discriminant function score. So I'm going to call this discriminant function y. Now, what I do now is I go in and start looking for discriminant function scores here, and it looks like to me that that positive scores indicate classification of A and C looks like it's larger. All right, I don't know if this is going to let me do this or not, but let's just look at a box plot. This may actually be kind of clever. If we do y across class, it may give us good cutoffs. So it looks like to be classified in group A, that you're going to need a positive discriminant score. It looks like, although there's a little bit of overlap, it looks like that to be classified in group B, that you're going to need somewhere about a -6 up to 0. And to be classified in group C, you're going to need somewhere about -6 and below. Now there's one outlier there. We may really kind of want to get in on that person and may possibly delete them. But I'm kind of confused why that person exists. Okay, well, it's a misclassification, obviously, but there seems to be a pretty clear distinction between So anyway, we get a classification, or I'm sorry, a discriminant score of positive. There's no question. We're going to predict group membership for A for that one. For B, let's try this. T apply, Y class, and let's do the min value. And let's do T apply, let's do the max value. All right, so it looks like the classification for A uh, 3.5 and 7.7. So we'll classify a person as B if their discriminant score is between, say, -1.6 and, well, so let's do this correctly, -6.61 and negative 1.63. And we'll classify a person as C if their discriminant score is between negative 11.3 and negative, say, 5.9. Okay? Now, example. Someone comes to us I'm just making this stuff up, so it'll probably bite me in the tail. So what would be their predicted group membership? Well, guys, as you would expect, what we will do is go up here and put in their information. I'm just going to do this as Y new. So their X1 score is 4.5. Their X2 score is 3.1. Their X3 is 3.8. And X4 is 1.1. So Y new, this person has a negative 2.97. So negative 2.97 falls in this range. So I would classify this person as group B. Now, does it mean we got it right? It doesn't mean we got it right. But, based on our model, that's what the correct classification would be. All right? So, gang, that's the end. That's not only the end of this video, it's the end of all the new topics I'm going to give you in 6610, 6620. I truly think you're ready to dive in and start doing some quantitative research now. One thing I'm going to warn you about, don't let the cart drive the horse. Let the horse pull the cart. Don't go into your research thinking, you know what, I like that discriminant function analysis stuff you told me. That's what I want to use on my master's thesis. We'll learn all about that. You're gonna learn to create research hypotheses and research questions, and then the statistical process or statistical techniques that you use evolve naturally from the hypothesis that you set up and wish to test. What's the intent of your study? So it's tempting at this stage, because I know I went through it a few years ago, well, many years ago, when I was doing my PhD. It's so tempting to think that the statistical process is going to drive the goals of the study, and that's just not the case. So, gang, that's all I got. Your final project should be up soon. Take care.